Greetings, it's Paul Bamberg with the introductory video for Class 17 of Math 117. And we're going to be talking about the laws for conditional expectation and then applying them to a two-step call option. So, we start out with two things, a random variable, I'll call it capital X, and a partition of the sample space. I'm going to assume there's a countable number of events in the partition, and these generate a sigma field, which we'll call G. The conditional expectation, X conditioned on this sigma field, is a new random variable. It's not hard to prove, though we're going to skip the proof, that it's integrable. And let me remind you what the rule is for evaluating this random variable. It's a function, remember, and when we evaluate it on an element omega of the sample space, the way we do it is we figure out which event in the partition omega belongs to, and then we take the expected value of x over that partition, and that replaces the value of x on omega itself. So it's sort of averaging out over the partition. Here's an example that I'm going to be using on the next page to illustrate this. The experiment is we roll a fair die and we toss a fair coin. That means there are 12 elements in the sample space. A typical element would be a 3 on the die and the coin comes up heads. The random variable x will simply be the number on the die. That is, it will assign to 3 and heads the number 3. The random variable y is determined solely by the die roll. It has the value 1 if you roll a 1, 2, or 3, 2 if you roll a 4 or 5, 3 if you roll a 6. And the partition we're going to use is the sigma field that's generated by this, the level sets of y. So G1 will be 1, 2, 3, G2 will be 4, 5, and G3 will be 6. The notation, expectation of x conditioned on G and expectation of x conditioned on y are the same. And as I said in the last introductory video, anytime you have a random variable whose level sets generate the partition, the conventional thing to do is just say you're conditioning on that random variable. Law 0, which isn't explicitly stated in Deneen, is that if you condition a random variable on itself, that changes nothing. And the reason is extremely simple. The way the partition is defined, y is already constant on the partition. So when you average over all the values for a specific event in the partition, the values in that event are all equal to start with. It doesn't change anything. Slightly more subtle laws. The first law is always called taking out what is known. And what it means is you can factor out anything that's already constant on each event in the partition. This means, for example, that if you're taking the expectation of y times x conditioned on G, you can pull the y out. And the reason is that on any element in the partition, y is going to be constant. So if, for example, we're evaluating this on an omega, like roll of 2 combined with heads, what we have to do is take the average over the event in the partition where y equals 1, and it makes no difference whether we do that before or after calculating the expectation. The easy way to do it is first calculate the expectation of x over that element in the partition to get 2, and then multiply by y, which happens to equal 1. Law number 2 is generally stated as independence drops out. And what it says is if you condition on a sigma field where every event in the partition is independent of x, that is, independent of anything in the sigma field generated by x, you get a new random variable that has the constant value, the expectation of x. In our example, we can do this by conditioning on the event the coin comes up heads or the coin comes up tails. And let's think about what would happen then if we're conditioning x on g. We pick an omega like 2 and heads that leads to event g1 in the partition. And what we have to do when we condition on heads is just average over the 1, 2, and 3 that combine with heads. But of course, that's exactly the same on conditioning on the event 1, 2, 3, whether combined with heads or to tails. So the independent event drops out. The third law, and you will be doing a more formal proof of these on your own, is generally known as the Tower law. This says, suppose that G is a finer partition than H. In that case, it doesn't make any difference if you condition on G before you condition on H. You can write this very formally as the conditional expectation of the conditional expectation of x conditioned on G conditioned on H is just the same as the expectation of x conditioned on H. As a concrete example of this simple-minded but difficult to understand rule, suppose that the sigma field H is generated by 1, 2, 3, and 4, 5, 6. To get G, of course, we will split up 4, 5, 6 into two events, one of them being 4, 5, and the other being 6. Let's suppose that omega equals 2. Now that's a little imprecise. I should say omega equals, for example, 2 combined with heads on the coin. And there are two ways of calculating this. The simpler way is just to take the expectation over the set of 6 events, 1, 2, and 3 combined with heads and tails, that includes our event where omega equals 2. The more complicated way is first we condition on G, and if we have an event G2, which was just 1, 2, we'd end up averaging over 1 and 2 and then combining with 3. We end up with the same result either way. Now let's go back to call options. For the sake of concreteness, let's convert all monetary values back to time 0. So the price random variables can be a y0, which is the same thing as x0, y0, y sub t, which is the value at time 0 of the random variable that gives the value at time t, and something very similar for capital T. y0, of course, is a constant random variable for the simple reason that the sigma field is what Deneen calls F sub empty set. It's the sigma field that includes nothing but the entire sample space and the empty set. And we have the expectation of y sub capital T conditioned on that is the same as what we get by first conditioning on F sub t, and that's just the expectation of y sub t conditioned on the sigma field F0. It's just y0. We can do the same thing with the random variables that give the value of the option. We used to call those v0, vt at time t, and v sub capital T at time capital T, but when we multiply them by the appropriate discounting factors, we'll give them new names, z, And our criterion for pricing the option is that the expectation of z sub t conditioned on the events for time 0, namely the entire sample space or the empty set, is the same thing as z0. Let's get into something with a little more content now. Remember that for a single step call option, we figured out that by buying or selling an appropriate number of shares of the underlying scratch ticket, it was always possible to design a perfect hedge for a call option. Now we're going to do the same thing for a two-step call option. Here's the diagram for the per sell call option, which we'll deal with first because we don't have the complication of having to discount future values. In order to do this, we work backwards in time. So we will suppose that you've sold a call option with a strike price of 26. Having sold a call option, you are in trouble if the value of the scratch ticket goes up, and you're going to hedge your position by holding a certain number of shares. We'll continue to call that delta. Now let's think about what can happen on day one. On day one, the scratch may have led to node C. The share price has dropped to 15, and there's no way it can ever get above the strike price. In that case, the option's never going to have any value. You don't have to worry about hedging, so in that case, you choose to hold 0 shares. The other more interesting possibility is the one where the share price has gone up to 30. That means it can do one of two things on commencement day. Either it can go up to 35, in which case the option will be worth 35 minus 26 or 9, or it can go down to 20, in which case the option will become worthless. Let's call the number of shares we're going to hold delta 1, and we're going to choose delta 1 so that our loss is the same in both cases. If the shares go down by 10, which means the option becomes worthless, then we lose 10 times the fraction of a share that we bought. If the shares go up by 5, we lose 9 because we have to pay off the call option. On the other hand, that loss is partially mitigated by the fact that the delta 1 shares we bought have gone up in value by 5. This turns into 15, delta 1 equals 9, or delta 1 equals 3/5. We can figure out our loss in either case. Probably the easiest way to do it is to say if we have 3/5 of a share when they go down, we lose 3/5 of 10, or 6. So we conclude that the current value of the option when we're in state B here is 6. We reached the same conclusion earlier by looking at things from the buyer's point of view in terms of probability. Now we'll go back to day 0. On day 0, we see that there are two possibilities. Either the scratch can make the value increase, in which case the option, as we just calculated, will become worth 6, or the price will go down to 15 and the option will become worthless. So, as before, we choose a number of shares delta 0 so that what we lose if the shares go down, namely 5 times the number of shares we buy, is the same as what we lose if the value of the option goes up. We now lose 6 because it becomes worth 6, but that's mitigated by the gain resulting from our delta 0 shares having gone up in price by 10. This time 15 delta 0 is equal 6. Delta 0 is 2/5. In either case, we are going to lose 2, and therefore that's the current value of the option. If we sold the option for 2, after losing this 2, we'd break even. So we got the same calculation as from the buyer's point of view. So now we have our complete hedging strategy. Having sold this option, we hedge it on day 1 by purchasing 0.4 shares. At a fair market price of 20, that'll cost us $8. If the share price goes down, we sell these shares because we don't want to hold anymore, and in doing that, we lose $2. If, on the other hand, on day 1, the price goes up, now we need to hold 0.6 shares, so we buy an extra 0.2 shares. That'll cost us $6 at $30. Now we send a total of 14. Now we've got to consider what happens on day 2. If the price goes down, we breathe a sigh of relief. We don't have to pay off the option, and we still got these shares, which we can sell for $12. We spent 14, sold the shares for 12, and we lost $2. If the price goes up to 35, well, we can sell the shares. 0.6 of a share at 35 will net us $21. We've already spent $14. We have to use $9 to pay off the option, so we spent $23, but we just gained $21. Our net loss is $2. So notice that by carefully setting up and readjusting the right portfolio, we can guarantee that having sold this option for $2, we end up paying out $2 some way or another. Where are we going to go from here? Well, you've seen that if we have information at one intermediate time, then we have to compute conditional expectations twice. If we have intermediate information at more than one time, the computation becomes messier in detail, but there are no new ideas. What will introduce complications is trying to pass to the limit where the price changes continuously. So here are some ideas that are going to show up in the next couple of weeks. Notice that at each step, the expected value of the option doesn't change. A process that has that property is known as a martingale. Martingales are discussed in Chapter 9 of Deneen. We're going to do discrete ones in the next class, continuous ones in the class after that. If we have more and more situations where the price can change, the price changes will be smaller and smaller. If you think about the central limit theorem, you might say, oh, this is going to involve some sort of e to the minus x squared density function. That's right, we'll get a normal distribution, and we will invent the so-called Wiener process. If we work backwards from the maturity date and use conditional expectation with probabilities to calculate the fair price, we will end up with the famous Black-Scholes formula for pricing options. And if we extend the hedging strategy that I just introduced to the continuous case, which means we constantly adjust our portfolio, that's going to require that we develop the Black-Scholes partial differential equation. The Black-Scholes formula and differential equation will be the topic of the last couple of weeks in this course. So with those comments, I am done for the day.